the introduction and the invitation to speak here. I'm always glad to come do math in my favorite city. So thanks all for the invitation. Yeah, so I'm going to tell you about, I guess in the title I said interpolation categories for conformal embeddings. Here I said quantum subgroups. You'll see later on they're very closely related stuff. So this is all joint work with Kane, Michel, and Hans Wenzel. If you would like to be able to go backwards in the slides, all the slides for my talk are on my website, which you can find here. You used to be able to find it by Googling my name, but Google is broken now and no longer returns my website. So I will pause for one moment if anyone wants to go there. But all right, great. So, So this talk is going to have three parts. I have to tell you about interpolating quantum subgroups. So first I have to tell you what I mean by interpolating. Then I have to tell you what I mean by quantum subgroups. And then I'll get to a new interpolation category. And I should say, you know, in the partial theme of the day, there will be some defects. You know, there's going to be some theory on a border of another theory. So hopefully that means it fits okay with the topic of the conference. All right, so delete interpolation, the idea of this is you start with some discrete family of tensor categories. So the examples you should have in mind is something like rep GLN. For each n, you get a nice category rep GLN, and the Hom spaces stabilize as n changes. That's essentially Sure-Weil duality. Sure-Weil duality says that the Hom spaces between tensor powers of the defining representation of GLN end up looking like the symmetric group, the group ring of the symmetric group. So they kind of stabilize. So, and the idea is if you're in this setup, you should be able to build a continuous family of tensor categories, CT, which in some sense interpolates between your discrete things. So there's going to be a bunch of examples of this, like GLT, OT, ST, those are symmetric groups. They're quantum versions of GLT and OT. And I'm going to tell you a little bit about that idea now, and the main goal of the talk will be to do a delete interpolation for something a bit weirder and new. Okay, so I want to tell you what GLT and OT are. So in order to motivate GLT, I want to tell you what GLN is in a slightly weird way. So GLN is the boringest group that has a representation of dimension n. If all you know about a group is that it has a representation of dimension n, that group is GLN. Okay, ON is the boringest group with a self-dual representation of dimension n. Okay, I need this symmetrically self-dual so that's orthogonal and not symplectic, but that's what ON is. Okay, and the idea is a group has a category of representations that's a symmetric tensor category. So I'm going to generalize from groups to symmetric tensor categories. And so I just want to generalize this notion that GLN is the universal group with a representation of dimension n. I want to say one more thing before I go to the next slide. GLT is going to be the universal tensor category with an object of dimension t. Universal symmetric tensor category with an object of dimension t. Okay. Now,
question already?
Yes, question.
Is this over the complex numbers, everything?
Yeah, I'll be working over the complex numbers. There are versions of this over other fields, but I'll just be over the complex numbers. Yeah. Okay. It gets much harder over finite fields.
What about over the reals?
There's probably some kind of real structure on it when t is a real number. So, but you're still looking at complex representations. So, So I want to use this idea that GLT is the universal symmetric tensor category with an object of dimension t to describe it. So I'm going to use the graphical calculus, the pictures, the kind of that you get for symmetric tensor categories to describe what these look like. I'm going to do it for OT first because it's a little bit nicer. So OT, this means diagrammatic version because there's going to be a slightly different version I'll mention on the next slide. The diagrammatic version of OT is the symmetric tensor categories whose morphisms look like linear combinations of pictures like this. These are the pictures that I can draw in any symmetric tensor category, modulo the relation saying the dimension of that object, that's the circle labeled with that object, is t. Okay, and this defines a category, this is a morphism in Homs from 2 points, which you're supposed to think of as the generator squared, to 4 points, the generator to the 4th power. Okay. GLT is the same thing, but with oriented strands. Okay. All right. So that's what OT and GLT are. They're just the objects are just, you pick an integer and that tells you like which power of X, or for GL, maybe you have to pick how many are X's and how many are X duals. Those tell you the orientation. And then you look at linear combinations of maps like this modulo just this relation. Okay. All right. Let me give you a couple warnings about this. The diagram version of GLN, that is to say when T is an integer N, does map to rep GLN, but that map is not an equivalence. And the reason is that in GLN, the n plus first wedge power of V is trivial. And in my setup, I mean, that I can't make sense of that for general T. I can't take a Tth wedge power of something. I can only take integer wedge powers. And so I don't see anything like that in the diagrammatic version. This shouldn't surprise you because I can tell you a bunch of other symmetric tensor categories with an object of dimension T, with the object of dimension N, namely the Lie supergroup categories coming from rep GLN plus KK. The Ks cancel when you take dimensions. And so those are also symmetric tensor categories with an object of dimension N. So GLN diagrammatic has to also map to all of those. Yeah. Yeah.
I could have imagined a story that if I was really good at little categories, I'd be able to get both sort of both traces of the n plus k bar k dimensional things.
Yeah. That's a good question. I don't have a good answer. Maybe we'll talk afterwards. Yeah. Okay, so if n is an integer, there is also an abelian version of GLN that's a bit fancier, and I'm not going to need this in my talk, but just for your general like education, if you read about interpolation categories, there's like easier stuff that involves just this game theory, and then there's hard stuff that involves abelianization. So if n is not an integer, the abelianization is very easy. It's a semi-simple category, and you can just make it abelian by doing some kind of completion by projections. But if n is an integer, there's a much harder thing called GLN abelianization. And in this case, you can kind of realize it as an inverse limit of these supercategories. Yeah.
What you just said makes me want to ask the following question. When you're doing GLN, are you doing any kind of Cauchy completion, or is it just the pictures?
Yeah, I should do I should do a Cauchy completion. Yeah, exactly. Yep. Yep. Okay, so you can realize these weird abelian things as some kind of inverse limit of these supercategories. That's a construction by these people, but we won't need it for my talk. Okay. I just wanted you to be aware that there's a harder thing out there that's the abelian version, and there's a lot of work in that direction.
Are you saying here that there's a unique abelianization or no?
In these cases, I think there is, but I don't know that there's a general theorem in that direction.
Does that abelianization have a universal property of being?
Yes, exactly. It's for faithful maps out of it. Of course, the semi-simplification is also a map to an abelian category, but it's not faithful. So it's universal for faithful maps to abelian. These are categories. Okay, so there's also a quantum version of this whole story. You can talk about just like rep ON deforms to ONQ. Let me make a little bit of a remark here. I really want here the category that Q deforms rep ON, the group, not SON, not spin N. I really want ON here. Okay, so so that means you're only looking at the vector representations, not the spin representations. And if what you're used to is SON, you have to equivariantize by some Z mod 2 to get the ON version. But I really want the category that deforms ON. That's going to be something called ONQ. There's similarly something that deforms GLN called GLNQ. And I can also interpolate between these. And this is something not new. This is going to be something you're extremely familiar with, because Reshetik and Turayev says anytime you have braided tensor categories, you get a not polynomial out of it. Here I have a 2-parameter family of braided tensor categories, so I should get a 2-variable knot polynomial. And we know 2 different 2-variable knot polynomials, Homfly and Kaufman polynomial. And Homfly is just is the knot invariant coming from GLTQ, and Kaufman is the one coming from OTQ. So for example, here's a definition of what OTQ is. Define the BMW category to be the braided tensor category of sums of unoriented tangles modulo these skein relations. And if you pick the sign to be negative, so that it actually deforms overcrossing minus undercrossing equals 0, I pick the sign to be negative, and then I pick A and Z to be some sensible formulas in terms of Q. So one of them is some power of Q, and the other one is Q minus Q inverse. Then I will get some nice Q deformation of OT. And you can think of these as interpolation categories between the quantum moments. Okay, so there's just some change of variables here. This is just because people have different conventions for Q. So this is the right convention for Q for the formulas that I wrote down, but it's not important. Okay. Yes. Sorry, say again?
I would expect that this is T, the sort of thought and things that T was like a dimension or something.
No, it's Q to the T. Yeah. That's yeah. Let's see if I can explain why. I mean, one reason, why is
Quantum dimension is like Q to the N minus Q and
So you're saying that like actually one is.
you just look at this relation here. Theo, look at that relation. You know that that should be Q to some power involving N. All right. So let me just summarize some key ideas about deformation categories. A good way to get a Deligne interpolation category is to have some kind of uniform skein theoretic description, just like the BMWs give a skein theoretic description for all of the type O, for all of the ONs. That's what lets us write down this interpolation category. This I didn't talk about yet, but usually if I write down some random skein theory, I write down some pictures mod some relations, or it doesn't even have to be pictures mod relations. I write down any mathematical object that's given by generators and relations. It is often extremely difficult to show that it is not 0. Okay? And so if I just wrote down some skein theory, I have no idea whether I got something interesting or I just wrote down too many relations and it became 0. But here you're able to show that the skein theory is consistent for the whole family because it has these infinitely many quotients. Okay, so you check that it has at the special values, you know it has quotients to these things that you know to exist. And this not only gives you that the theory is kind of consistent at those points, because there are infinitely many of them, it actually gives you consistency on the whole line. And the reason is that to see that you have some basis, you're doing some calculation that only involves rational functions with specified denominators. And if you have an identity of rational functions that holds at infinitely many values, it has to be an identity. And so it has to work for all values. Okay, so there's this sort of hack that if you're trying to build an interpolation category between infinitely many things that you know to exist, you'll actually get this consistency for the whole family. And finally, I want one more moral, which is you should avoid determinants. So if I tried to give a definition of SLT, I would fail. And the reason is that in SLN, the nth wedge power is trivial. So I have to add a map from the nth wedge power to the trivial. That's a map that has n inputs and no output. But that varies as n varies. So I can't write down something uniform. I can't make the number of strands that come in not an integer. So I can't do anything like SL. Similarly, I can't do anything like the alternating group. Okay, so you often have to banish some determinants in order to make your deformation categories work. Okay, so that's the first third of the talk. Now I want to tell you about quantum subgroups. Okay, and this is, I think, you know, these quantum subgroups are in a lot of ways very close to the you know, the kind of things that the science collaboration thinks about, in that they are some kind of boundary of some larger. Okay, so I'm going to tell you about something called quantum subgroups. I'm only going to tell you about the type 1 ones, and I know this from old subfactor work of Akmianu in the 80s. Okay, so if A is a braided tensor category, so there are two ways to think about those kind of geometrically. You can think it's an E2 algebra, that is to say, your objects can be multiplied by putting them in the plane, and so that's why they're braided, because I can move them past each other. Or you can put in the categorical or time dimension, and then you get string diagrams in 3 dimensions, where your objects are on the bottom, your morphisms in the category direction go up in this direction, and you get a kind of a 3-dimensional picture, okay? So this suggests a good notion of what an E1 module for such a thing is. So if you think about it in this picture, it's you have some kind of stratified manifold here. We had a talk earlier in this week where we had these pictures. Now I've forgotten who, but
Jenny's talk this morning.
what?
Jenny's talk.
Yeah, but there was also an anyway, but yeah, also in Jenny's talk this morning. Yeah. So right, there was that. Yeah, but anyway. Yeah, so you can draw these kinds of pictures and these kinds of pictures. These are the ones that don't have the category dimension in. They make sense for any E2 algebras. And these ones only make sense for E2 algebras in categories, that is, braided tensor categories. But what you want to do is look at, okay, now I can have objects in C and objects in A, and I can multiply, if I have a bunch of objects in A and a bunch of objects in C, I can multiply them all together in a way that's well defined, and that tells you the right interaction between the tensor product on C and the braiding in A. And the same way, and this one really, yeah, is exactly like in Jenny's talk, pictures like this that are modules for a braided tensor. There's another way of thinking about this, which is not I don't think original to us, but you can read about in our paper with David and Adrian, which is that the action of this is the same thing as giving a map from A to the center of C.
Sorry, I'm confused about this SL thing. So
Yeah.
if I present SL2, we like temporally leave or something,
Yeah.
and I don't really see this determinate constraint inside of the diagram.
Right, but there you don't have the T variable, you only have the Q variable, right? So you can, yeah, so I want to change 2, I don't want to change Q, yeah. Yep. Okay, any questions about that? There's something else called type 2 quantum subgroups, which I won't care about, which is where you forget the braiding and only look at the notion of module for a not braided category. All right, and I'll need one more thing. This is kind of, there's a general notion called Bar-Beck due to Beck. The version Ostrich kind of introduced this stuff to tensor category settings, which is anytime you have an external thing, so you have like a 3-dimensional thing acting on a 2-dimensional thing, something like that. In addition to having an external description like that, there's an internal description in terms of some kind of algebra inside the thing that's acting, okay? And in this case, what that looks like, and this is always described by like composing something with an adjoint. So what happens is I have this map from A to the center of C. I can take its adjoint and I can see where the unit goes, and that's going to give me some algebra, and this algebra will be very nice. It's going to be what's called an étale algebra, meaning it's commutative and semi-simple and finite dimensional, and C is going to be the category of A modules in A. Okay, so another way people talk about quantum subgroups is they just say it's just an étale algebra in a braided tensor category. Okay. But I care not just about this étale algebra, I really care about the thing that I can draw on the boundary, which is the category of A modules for that algebra, okay? All right. So let me give you some examples of this. So if A is quantum SU2 at a root of unity, there's a classification of all of the type 1 quantum subgroups given by Dinkin diagrams, not all of them. Yes.
Okay.
That's right, just need to see one.
Okay, so then quantum subgroups are classified by ADE type Dinkin diagrams that look like not quite all of them. There's the A's, there's the D evens and the E evens. You don't get the odds. The odds correspond to type 2 quantum subgroups. Okay, that have the right Coxeter number. So let me explain where these graphs come from. The vertices of the graphs are the simple objects in C. And the edges tell you the fusion rules for acting by the two-dimensional representation of SU2. Okay? And if you know what root of unity you're at, that gives you some constraints on the eigenvalues, right? Because you know the dimension of that object, so that tells you the eigenvalue for its action. And so it can only be a Dinkin diagram that has the right Coxeter number for that root of unity. Okay? So different type Ds are going to correspond to different roots of unity. And this goes all the way back to subfactor stuff of Jones and Agnianu in the 80s. In the tensor category language, you can see this in an old paper of Pirlov and Ostrich. Let me give you some examples of what I mean by that. So I could look at A4. This is SU2 at a 10th root of unity. Why is it a 10th root of unity? This has dimension quantum 1, 2, 3, 4. So the next guy, quantum 5, should be 0. And that tells you how to do this translation. This is level 3. So you will go completely insane. Level 3, 4 vertices. 5th will really, 5th-ish roots of unity. There's an annoying shift here. It will drive you crazy for your entire life. Okay. This one only has the trivial subgroup A4. That's the only thing with the correct Coxeter thing. The trivial subgroup is just, I take my braided tensor category, I forget that it's braided, and I have it act on itself by just tensoring. So that one's always there, and that's it. But if I look at this guy, this A5, when Q is a 12th root of unity, level 4, then this one can act on D4. So that's going to be some tensor category with 4 simple objects. And if I tensor with the two-dimensional, it does this kind of a thing. The algebra sits out at the ends here. And this category is just the category of modules for that algebra, which essentially folds it in half. The modules for that algebra, there's a module that's the sum of these two. There's a module that's the sum of these two. And then there's 2 different ways to put a module structure on the guy in the middle. And that gives you these 2 things. Yeah.
Just nudge you to remind about finite subgroups of SL2. I mean, you're taking for granted that everybody is.
No, that's a great point. So you could do the exact same thing for subgroups of honest SL2 when Q is 1. And you could ask about subgroups of that. So that's like, I mean, honest subgroups correspond to when they're both symmetric. I could also do some version where it's symmetric and braided, which would be some kind of type 2 subgroup. But okay, so I have a symmetric tensor category acting on another symmetric tensor category that's SU2, honest SU2. There, the subgroups are actually subgroups. And they're classified by affine ADE Dinkin diagrams, and this is called the Mackay correspondence. Thanks. Yeah.
So I understand that in that case, you take the representations of the finite subgroup.
Yeah.
And your fundamental representation restricts to one of those, and so that's how you.
Yeah, exactly. You just restrict in tensor.
Yeah.
And the rules for restricting and tensoring are given exactly by this.
And that remembers the group.
Say again?
That remembers the subgroup.
You have to be a little bit careful, I think, depending upon, and this was where I was getting confused about whether I want the thing that it's acting on to be symmetric or just tensor or what. I think there are versions where you can put a little co-cycle twist, and so it might not be completely determined by the Dinkin diagram. I also always get confused about in what circumstances I need 2 versions of E6 and 2 versions of E8. Maybe I need 2 versions of E6 and E8. No, I don't. Dave is saying no. Great. Andre, you had a question? No. Okay. Any other questions? Oh, right. So I was going to say there's a weirder thing, which is I can take A11 and that one will have an E6. Right. So that's an example. Again, this is a 24th root of unity level 10. Great. So that's some examples. Now, you might ask, if I took some quantum group that wasn't SU2, do I have some similar classification like this? And so there's a result, some early ideas due to Agniano, and then a key contribution due to Andrew Choperet. And then the version I'm going to tell you about is Terry Gannon's. That's, well, it is better than Agniano's result in that it's actually written. It is, and it's better than Choperet's result in that it is more general, but is also better than both of their results in that it is more effective. Okay, so he says if you fix G and vary Q, then all but finally many quantum subgroups are what are called orbifolds. I was supposed to mention those on the last slide. That's stuff like D, where your algebra is just a bunch of invertibles that sit out on the corners. Okay, so those are the easy ones that you kind of always have. So you get stuff that looks like type D, and then the only ones left were E6 and E8, and that's the picture for every G. You get your orbifold ones that are kind of easy to understand, and then even as you vary, of course, for fixed Q, there's only going to be finitely many subgroups, but even as you vary Q, you only get finitely many exceptional ones that don't look like these type D. And he has a classification up to rank 6. It's effective enough that you can get a full classification up to rank 6.
Are that overall Q, there are finally many, or for each Q?
For all Q. It's easy to see that if you fix Q and G, that there are only finitely many module categories. That's some kind of Agniano rigidity type result. But as you vary Q, that's a deep result. Yeah. Yep. Great. Any other questions?
You're talking about for big or semi-simplified quantum groups when you.
Yeah. Semi-simplified quantum groups. Yeah, rigidity. Yep. But I don't think you need to assume that Q is like make parity assumptions on Q. You probably need to assume that Q is, well, you can of course throw out small values of Q, right? They'll only have. Okay. There is one last general thing I want to tell you about quantum subgroups before I switch to kind of special ones coming from conformal inclusions. And this is also very closely related to Jenny's talk this morning. I want to put something acting on the other side, okay? And well, in general, there could be many things you could put on the other side. That's like a bimodule. There are lots of bimodules out there, okay? But there's always like a best one, which is where you put the commutant over on the other side. And this one will often be invertible, okay? You need a little bit of theorems to say that it's invertible, but usually it is. So if M is a finitely generated projective A module, here M and A are just ordinary algebras and modules. I'm just motivating something from classical algebra. Then M as a bimodule between A and its commutant is always a Morita equivalence. Okay, and so I want to do the same thing here. I'm going to get some higher Morita equivalence that's called Witt equivalence. And I'm going to put A over here. I'm going to put C over here. I'm going to put some notion of commutant over there, which turns out to be the Muger centralizer of A in the center of C. That's one way of describing the thing that you put there. But you could also just literally interpret it this way if you know how to interpret all of the symbols. This will always be an invertible defect line. You usually would have thought I needed some, always is overstating it. Everything in my site has some finiteness properties. So it has some finiteness properties. That's like this finitely generated. You might think I need something like this projective, but rigidity actually guarantees, like rigidity is like finite dimensional C star algebras, all their modules are projective. Like if you have a rigid tensor category, you never have to worry about these kinds of extra adjectives. So this will always work. If I take a finite braided tensor category here, or at least a fusion one, and I put some fusion category here, and I put this there, that's always going to give me an invertible bimodule. This is very different from our talk this morning, where there are infinite categories, and so it's much less clear when things are invertible and when they're not. There's some unhappiness. What?
No degeneracy.
Yeah, you need to, yeah.
Oh, I need a faithfulness condition of A acting on C.
It's invertible over the Muger centralizer.
No, the legend.
Is this? No, this should be, oh yeah, I need some kind of faithfulness condition, but if A is fusion and not multi-fusion,
No, it's not enough.
not enough?
Oh, you need A to be non-degenerate.
Yeah, we need C to be non-zero.
It'll be invertible as
All right.
Over.
The people who care about this know the answer better than I do, and everyone else will hopefully not be bothered. All right, so in my case, it will be invertible. Maybe I need a mild additional condition. Okay, great. So,
And so what,
yes,
so A, in this picture, A is, sorry, C is, which one is the braided one? Which one is?
A is braided because it's two-dimensional. C is tensor because it's one-dimensional. So this guy will also be braided. Yep. Yeah, and the actions will commute in exactly the sense that they centralize each other in the center of C. Yep. Any questions about that? I'm about to shift, maybe my talk should have had 4 sections, because I'm about to shift from quantum subgroups in general to these very special quantum subgroups called conformal inclusions that come from conformal field theory. So where do you get quantum subgroups? The main source is these things called conformal inclusions or conformal embeddings, or there's some third synonym. And these can be set up in a lot of different ways. They sort of come from conformal field theory, so you can set them up in the language of VOAs or the language of nets of operator algebras or several different languages, but they kind of come from this world of CFTs and WZW models and loop groups and all of this, okay? And I don't understand this portion of the talk. So there'll be a couple of, hopefully everything I say will be true. But you don't actually need to understand it very well, both to read the paper, which should be out in the next month or so. I hoped it would be out by now, but it's not quite out yet. You don't need it to know much about these to read the paper. You don't even need to know much about it to write the paper, because none of us are experts on this. You need only the tiniest bit of this theory, but let me explain it to you. So if I start with G and some level, I get something VGK, okay? And it will have some category of modules that will be some braided tensor category CGK, okay? Andre is looking very grumpy. And this category, it will turn out by some results of Finkelberg and Kajdan Lustig, which have some small gaps in them. So you can see Andre asked the math overflow question, so you can find out if that's where I got this slide from. It's Andre's math overflow question. This category will actually agree with the category representations of the quantum group at a certain root of unity, which is like the relationship between the level and the root of unity. We know to be confusing because we already saw it was confusing for SU2. So there's some factor of 2 because I didn't write a 2 there. And there's some shift by the dual Coxeter number that explains those weird shifts we were seeing before. But these will always give you some category that's the same as the quantum group category, okay? It won't give you all the quantum group categories because here I really do want to take the root of unity closest to the axis, because that's the one that gives me unitary stuff. It will also not give me all roots of unity because of the factor of 2, but many quantum groups of roots of unity come from this construction, and the ones that do come from this construction, you can build quantum subgroups in a nice way. So a conformal inclusion is an inclusion of one VOA into the other with the same conformal vector, whatever that means. And what's important is that a VOA is in particular an algebra. And so you can think of W as an Étale algebra in Rep V. And moreover, if I have an Étale algebra in Rep V, the fact that Rep V came from a VOA and I have this algebra gives me enough information to construct an actual VOA coming from that algebra, okay? So what you're supposed to think is these kind of hard CFT questions are easy and finite extensions. That is to say, if I already have something where I've put this huge conformal field theory picture, and then I take some finite extension, those things I can just describe categorically with finite, with no hard infinite stuff going on, okay? So Étale algebras in Rep V just correspond to bigger VOAs with these conformal inclusions, okay? And moreover, the category of representations of the big VOA is, oh, I forgot to introduce this notation. We go back. 2 slides. I was talking about this invertible setup here, where I put end A of C over on this side. Remember I said everything has an external description and an internal description? The internal description of the thing that you put over here is something called the category of local modules. It's not all A modules, it's only the A modules that play well with the braiding in a very specific way. So that thing that goes on the other side is rep W, okay? But the thing that goes in the middle, A mod, is somewhat mysterious. Like you can't just read it off. I'm about to tell you some like examples of V's and W's, and I can read off the thing on the left, you read off the thing on the right. The thing in the middle is determined by all of that information. But if I wanted to say, ask what the fusion rules were, as far as I know, that's not just something. Okay. Great. So here's an example. The E6 quantum subgroup of SL2, which we already talked about, comes from a conformal inclusion of SL2 at level 10. So the thing on the left here is always going to be the right one, right? We were studying, you know, SL2 at level 10 was the thing that had the E6 subgroup. So the thing that goes on the left will always be the main thing acting. The thing that goes on the right will be this commuton. And here I put SP4 at level 1. The thing that goes on the right will always be level 1. It turns out, but this gives me the E6 thing. But if I want to read off that, oh, I'm supposed to be looking at level 10, I just look here. But if I want to read off that the fusion rules are given by E6, I don't know how to do that.
You're talking about the fusion rules for A mod, not loc.
Exactly, A mod, not loc. The local A modules are very easy. That's just this. But the non-local A modules are more subtle. Yeah. Questions, comments? Yeah.
I guess in this example, you're already saying that you're not always considering simple functions.
Right. Yeah. I'm interested in ones that are not simple currents. Yeah. Exactly. Yeah. Yeah. Simple current and orbifold are synonyms, right?
In the other direction.
There's another word that people.
This is when overfold takes you the other way. To the small.
Yeah, maybe. I was de-equivariantization is what I really meant. De-equivariantization should be, yeah, anyway, I think it means the same thing as simple current. Dave is looking very unhappy at me. What should I be saying right now?
It's just the orbifolds in simple current. De-equivariantization is the process of taking A mod anytime you have
Yeah.
an A looks like, you know, functions on your group, that it's orbifolds or simple current.
So it's been known for a long time, though you have to be careful because different people phrase the question slightly differently and have slightly different lists, and maybe they miss stuff, but it's been known for a long time, a list of all of these conformal inclusions, and you can go look them up. There's these old papers, and where I tend to look them up is this WIC group paper. It's not original to there, but they have a nice table. Yeah.
I'm gonna retract maybe what I said. You can de-equivariantize and also equivariantize.
Right, exactly, which I can in this thing. Yeah.
Then you're, yes, so.
Yeah. So at any rate, yeah, I meant to throw out all the simple currents. Those are the boring ones. I'm interested in the exceptional ones. Yeah. Okay, so there's a complete list of these Lie type conformal inclusions where on both sides I just have these VGKs. Okay. And this list has many weird exceptions, like this one. This one just sits there on a list on its own, and then next to it is some weirder one involving SL2 at some higher level, and that's it, and they're the exceptional ones, and they're weird. But there are also some infinite families, okay? Now, there are a bunch of infinite families that fall into this orbifold simple current de-equivariantization setting, and we don't care about them. So here is the list of families which aren't in that boring orbifold setting. There are 4 families. There are really maybe more than 4 because each of these families comes up twice in a way that are level rank dual to each other, and I don't want to double count them. So there are 4 families up to some sort of level rank duality where you get the same thing twice, and it's not that interesting.
just make sure to understand like the trajectory here. So we were interested in the quantum group setting, but then we moved into the VOA setting, and then I want to use, because vehicle
Yeah.
Lustig, and then I want to use that I can have everything be a VOA extension.
Yeah.
Yeah, okay.
So I'm gonna get a bunch of quantum subgroups this way. Here I have discrete families, and now I'm gonna try to interpolate between.
You're not including the two-parameter infinite families, like GLN cross GLM into GLN.
Yeah, this is that's a good question. Honestly, I just trusted Kane on this one, and I didn't look closely at what the other families might be. It may be that we're right, like we're not. Maybe we didn't look at ones that are. Yeah, I don't know. It's a good question that I should know and don't. Yeah, these are the families that we've thought about, great. So there are 4 families, right? You see they have this n, and the n is varying everywhere in sight. So I get a quantum subgroup of SL2, and then one of SL3, and then one of SL4, and the level is changing as I do that. So they fit into a family like this. And what so there are 4 of them. There's this one with SLN on both sides. There's this one where you have SLN level n and SO SLN. Yeah. Here I have SO n squared minus 1. That n squared minus 1 is just the dimension of SLN. Okay. And these other 2, the formulas here are kind of annoying, so I didn't write them down. They are also the dimension of the thing that I see on the left-hand side. Okay, so these are my 4 families. And what I want to do is build interpolation categories. Is there a delete interpolation for the determinant-free version of these discrete families? So there are lots of SLs and SOs on the previous slide, and I know as soon as I see SLs, there's going to be no hope, and I'm going to have to get rid of determinants in some way, but I get rid of the determinants, and then I want an interpolation category. So for the first family, the answer is already known to be yes by a result of Zhengwei Liu, where he did not set out to solve this problem. He was solving a scheme theory classification problem, found a 1-parameter family, and was like, where is this coming from? And worked backwards from the 1-parameter family to its relationship to these conformal inclusions. Okay, so it's a lovely paper and a lovely construction, but it's not so helpful to know how to generalize, right? It does, you know, like because like it came out of a different question rather than starting from this question, okay? And so in particular, we don't know how to adapt what he did to the other 2 settings. So I'm going to tell you about the second family in this talk. Everything that we do should work perfectly fine for the 3rd and 4th families. In fact, it works for the 3rd and 4th families at once. One thing that I didn't tell you was that the OT family at negative integers is related to symplectic groups. So in fact, the 3rd and 4th families here, where you have SO and symplectic here, actually they just fit into one continuous family where the positive ones are O's and the negative ones are symplectic. Okay, so that's our goal. And in the last 6 minutes, I will tell you about our new results. Any questions before I get to the new results? The idea here is extremely similar to Jenny's talk this morning, which is that we already know the skein theory on one side, we already know the skein theory on the other side, and we just have some limited interactions at the interface. So on the front, we put the Homfly category at the right values of the parameter. And it turns out the right values of the parameter, the way the 2 ends interact, this twist parameter is always I. And then there's an interesting Q factor here in the Hecker relation. So you just take the Homfly, that's just skeins modulo this Hecker relation, this twist relation, and a circle relation, and that's it. On the backside, depending upon parity, you might get a Z mod 2 cross Z mod 2 pointed category, or you might get Ising. But in either case, there's a Z mod 2 subcategory that has a very simple skein theory where you just use red strands that are, and I'm not even going to use the braiding on the back. I'm just going to use red strands. They recouple like this, and they have a circle that you can just remove. The reason I don't want to use braidings on the back is just that there's an interesting sign in the twist, and that will get you confused. Okay, so that's the idea, but the problem is they can also interact in the blue sheet. There is one easy way that they can interact in the blue sheet, which is that this invertible object G from the red part actually lands inside X tensor X dual for the defining representation of SLN. And this is a little calculation for which you actually need to know a little bit about VOAs. Okay? It's not that bad. You use Frobenius reciprocity, and you use that people have written down what 1 plus G looks like as an algebra, and you can read off that G sits inside X tensor X dual, and that gives me one interaction that can happen in the sheet. I can have a red thing coming in from the back, and it can hit two black things coming in from the front, okay? And what you're supposed to think here is that the red stuff is not so bad. The red stuff is very boring. And then if you ignore the red stuff, now it almost just looks like Homfly again. And that's why our lives are going to be easy. The interactions are extremely boring. All right. So I'm going to define a category to be the tensor category spanned by diagrams that I can make out of a red strand that's unoriented and a black strand that's oriented that are allowed to interact by those kind of vertices. And for technical reasons, to keep things simple, I'm only going to allow black strands on the outside, but this lets me define some category. So I look at pictures like this modulo some relations. So Rademeister 1 through 3 for the black strands. Homfly, those relations I wrote on the previous one. This guy is symmetrically self-dual. That's sort of needed for the red strands to even make sense. Some bygone relation. It's not hard to work out what the coefficient here has to be. You don't even really need to do a calculation. Here's the important thing. It's not a braided tensor category. The black category in the front is braided, but the thing in the middle is not braided. You can only move black strands over these interaction points and never under, because that's the red side. Red strands, you could move under them, but I'm not using the braiding on the red side. So the really important thing is I only use this to do red under black and not black over red. And then I need some other, this is just that invertibility relation. And this is obvious because it's a map from X tensor X dual to 0. I should have drawn inner orientations on a bunch of these pictures, but I didn't because I got lazy. Okay, so this is my category.
Say again why there's only one red line when you had these at 2 times at 2 and
Yeah, I could have put in another one if I wanted to. It turns out that all of the objects in the interface will be summands of tensor products of X's and X duals in just this one G. I could have put in a whole Ising category on the other side and I would get the same thing. It'll just make my life harder.
I see. So also you don't need to take into account the non-invertible in the easing category.
Yeah,
That's already
exactly. I only took the easiest part, and it's not obvious that all maps are made of this just one kind of interaction with this one other kind of particle on the backside. It just turns out to be true. Okay, so that's the definition of EQ, and here's our theorems. If Q is one of these special values, then the Cauchy completion of the semi-simplification of the de-equivariantization by the determinant of this category. So I have to complete it so that it has objects that are not just tensor powers of X. I have to semi-simplify, and then I want to put back in the determinants, and that's this de-equivariantization step. That category we call SEN agrees with the quantum subgroup category. It is the category that sits on this boundary. Okay. And if I look at endomorphisms in this EQ category of X to the N, the dimension of that space is given by 2 to the N minus 1 times N factorial, which is not 0. And in particular, I've written down an interesting non-trivial Deligne interpolation category for you. And I can say a little bit about the proofs. So to get a map from SEN to these categories living on the boundary is relatively easy because I basically told you how it all works. Like there is that interaction. You have to prove that all those relations hold, but they're all such easy relations that there's very little to do. So that functor is very easy. What's hard is why it's full and faithful. The reason it's full is that it's this category is manifestly acted on by Homfly because the action on Homfly is just using pictures with only black strands. So it's manifestly acted on by Homfly. So it has to come from some quantum subgroup of that Honfly category, which is going to be a subalgebra of the thing that I want. And then, well, what we end up doing in the paper is just saying, someone's already written a paper about what all the subalgebras are. So it's relatively easy to figure out what it is. There's a more conceptual thing that I got from conversations with Andre, which is that because it's this 1 plus G is the free fermion algebra, all you're using is that as soon as it has G in it, G generates the free fermion algebra, and so it can't help but be the whole thing. But either way, you do an argument in terms of kind of the structure of this algebra A, where you need to know a little bit about VOAs to get that. And then it's faithful by semi-simplification and the fact that Cn is unitary. So the only hard part is this part. The proof of 2, you show by some evaluation algorithm that looks, some skein theory argument that looks like the Honfly argument, that you have some set of diagrams which spans and has the right size. So some set of diagrams that span and has the right size. And then I want to show that they're linearly independent. And I do that by saying that they're linearly independent in this quotient, Cn, for n large enough. They might not be linearly independent for the small n, but eventually, as n gets big enough, they become linearly independent. And so if they're linearly independent for infinitely many specializations, they're linearly independent. And then, yeah, one last thing, and this is where Hans got involved. So Kane and I, everything we did up to here was Kane and my work, and then Hans got involved. This is all kind of his stuff. He realized endomorphism of x to the n is actually a previously well-studied algebra called the Hecke-Clifford algebra that comes up in Sergeyev duality in the study of type Q quantum supergroups. From the fact that these algebras are well studied, you can actually read off the representations. So we can read off from that the classification of simples in these algebras, the dimensions of simples, the basic fusion rules using existing results about this algebra. And in particular, you know, I never feel good about a talk unless I have some insanely large diagram or table. So here's what it is for this. If n is 5, these are the fusion rules for this thing on the middle that I said weren't easy to read off. And what you do is there's a vertex for every strict partition. That's partitions where every length is different. And the edges come from ways to add a square. Add a square or add 4 squares corresponding to the dual. Okay, so I can go from here, I can add a square and get there. I could add 4 squares and get there. From here, I can add a square or 4 squares. And then if the number of rows is even, you also need a sign. All of this is stuff that people know from Sergeyev. So we can adapt this to other families. For the Liu one, the interesting thing is that it changes orientation at the interaction point, but otherwise things work kind of similarly. You could try asking about this for exceptional Lie algebras. So Kane has a student, Caleb Hill, who's working on this for G2 and has some good results about this conformal inclusion for G2. You might ask about the abelian version, and you might want to better understand this relationship to the isomerically superalgebra. I will not do the bonus slide. Thank you.
So you had to get the VOA picture, you had to reintroduce the determinants. Is there like a VOA? I think maybe somebody asked it already. Is there a VOA picture where you just work with?
Yeah, there should be. We don't do this because we're afraid of VOAs, but the principled way to do this. This is a vocabulary that I like. So chess players have they say the principled approach in this position, which is not the practical one. It's the one that is what the position is telling you. So the principled approach here is to start over again and make sure you did all of your conformal inclusions with GL and O to begin with. And surely you can do that, and things will be cleaner, and then you don't have to worry about this determinant issue. We were weak and didn't know about VOAs, and so we didn't do this because we wanted to use results off the shelf from the literature. But absolutely, you should be able to do all this in GL. And if you want to do the abelian version, you should do it all in characteristic P, which anyway, but yeah.
Do we get continuous families of VOAs?
This is, yeah, that's a good question. I mean, yeah, so you could ask, is there some sort of interpolation between VOAs? I have no idea.
Like infinite mini simple or something like that. They're not a moderate growth, right?
Yeah, that's right. They do get a lot bigger. So these interpolation categories, the combinatorics of the interpolation category at generic value of the parameter, have, look like the large N limit of the family. So they have much more HOMs than,
It can be hard to make such a category via a vertex operator.
Unitarity in the interpolated
Oh,
categories.
no, you almost never get a unitarity in the interpolated categories because the dimensions will no longer be positive, right? Because what usually happens, you have some dimension that's given by some polynomial, by maybe some rational function, and eventually when I plug in things, it'll become negative, but you semi-simplify and get rid of all the ones where it became negative. So yeah, generic values, you almost never get any kind of unitarity.
Right, so you got lost in the which parameters appear, so you have a continuous family like GLT.
Yeah.
So there's the parameter that's sort of the rank.
Yeah.
Associated to the rank of the.
Yeah.
These module categories that you're constructing, is that an additional parameters worth of module categories for each T, or is it somehow?
No,
more
I've
like?
essentially lost the parameter. So this kind of category would have two parameters, one corresponding to the rank and one corresponding to the level. But in this family, it only works if I have a particular relation between the rank and the level. So HOMFly is a two-variable thing. I am only constructing a category on which HOMFly acts on a one-parameter subspace of that two-parameter space. And yeah, and so that's why I only wrote down Q. I didn't write down Q and N, but there is a specified relationship between them that makes this family work. And this was what I was indicating. It's kind of nice, actually. The particular relation just makes the twist I. Like, it turns out that in this family, if you look at Q is some root of unity depending on N, and I take some power depending on N, those dependencies actually cancel, and the twist is just always I. So that's essentially inside the two-parameter HOMFly space. I take the subspace that is just things where twist is I, and those are the ones that I'm studying. Yeah. Yeah. Yeah, that's right. So I've thought about whether there is an interpolation category between quantum exceptional Lie algebras. But there the problem is you don't know whether it exists or not because you only have finitely many quotients instead of infinitely many quotients. So you don't know. If that family were to exist, you should be able to get a quantum subgroup categories also corresponding to the same, where did this, so this family that we're looking at all actually looks like VGH check sitting inside SOG1. And you could do that for any Lie algebra, including the exceptional ones. And if there is a family of exceptional ones, you should be able to interpolate between them like this. It would be slightly more annoying because you have a trivalent, like you have more maps inside the exceptional Lie algebra, but it's probably, it's probably doable. Yeah. And in fact, if you believe in the two-parameter Vogel plane of all Lie algebras, again, this is something you could write down for all of them. And so there should be some, interpolation category interpolating between all those quantum subgroups for all the algebras simultaneously, if you believe that conjecture. Yeah.
So when you were working with the finite categories, you get this split equivalence statement. And does that survive in some form for the?
Oh, that's a great question. So I definitely get a bimodule in the so for the interpolated category, I have HOMFly on one side. I have the sheet that is this thing I just described to you. And on the other side, I only have this Zmod. I have this Zmod 2. That is certainly a bimodule. I have no idea whether it should be invertible. I don't even know, like, I only have a Zmod 2 now on the other side instead of this Ising or Zmod 2 cross Zmod 2. I have no idea. It's a good question. It's certainly a bimodule. Whether it's invertible or not, absolutely no clue.
Sorry, I have very naive question. So for these embeddings, I think we can construct like a coset theory, a coset WCW, which should be like a TQFT, which because the central charge is 0. Is there some interpretation of this TQFT?
That's a good question. I've never really, coset constructions are one of these things that I have always struggled with a bit because you can't phrase them purely tensor categorically. You have to go into this VOA world. I don't know if someone who knows more about VOAs has some comment on this, but I don't.
When he's saying the coset VOA is trivial, and he also just keeps some TQFT.
It's a sort of roughly speaking descriptions.
Right, but A mod is exactly what I want on my sheet. Oh, so this is just like, what is the VOA description of the stuff on the sheet? I mean, it should be like bimodules for the.
I'm just saying something form.
Yeah.
What that said, like, said TFT. Is the TFT built from a mod as like it's the 11.1 TFT built from a mod?
Ah, yeah.
So that's just a formal statement.
I see. So that, but that is what I'm constructing here is.
No more questions? Thank no one.